Hey everyone, welcome back to 3 Deviations. In today's video of multivariable calculus, we want to discuss applying the chain rule. Now, what do I mean by applying the chain rule? Well, we're going to apply the chain rule to develop some more nuanced ideas of how we can take more generalized partial derivatives. And we are also going to discuss how we can apply the chain rule, the multivariable chain rule, into something very near and dear to our hearts in Calculus 1, which was implicit differentiation. It's actually going to seem a lot easier to you after I give you the definition. If you're a Calculus 1 student, you'll probably be fairly angry at me that I didn't tell you earlier this definition, because it would have made your lives a lot easier. Anyways, let's discuss applying the chain rule. So my first definition, I want to cover the two-variable case for the multivariable chain rule, and this extends to n variables as well. So let's say that z is some function of x and y, and then x itself is some function of s and t, and y is itself some function of s and t. So this is different because in the past we discussed x and y as being functions of t, and now these are functions of two variables. These could also be functions of three variables. This really does generalize very nicely for us. But anyways, given this, the rule for, so the derivative of z, so my function, with respect to one of these variables, s, note that these need to be partial derivatives now because these are both functions of two variables. So partial s, or partial z, partial s is now equal to partial f, partial x, partial s, plus partial f, partial y, partial s. You could probably tell if we had more variables in this function, how we'd just be adding more of these, then we'd be taking more partial derivatives. And note, I could, these s and t's, those could be intermediate variables themselves, and that would just mean you're multiplying more things to that factor, to each factor, right? So you're attaching more derivatives. Okay, so now I'd like to go through an example. But beforehand, obviously, you can see if I want to take the derivative with respect to the other variable, it's very similar. Anyways, let's try an example. So I'd like to differentiate the function u such that u is equal to x to the fourth, y plus y squared z cubed, if x is equal to rs e to the t. It almost looks like the word rest. This gets me a little sad because I want to take a rest. X equals rs e to the t, y equals rs squared e to the negative t, and z equals r squared s sine t. Okay, now how do we do this? Well, basically, our rule is to differentiate with respect to s, so we want to differentiate with respect to s, so we'll need to be a partial derivative. So if I want to find du ds, then that's going to need to be du dx, dx ds, plus du dy, dy ds, plus du dz, dz ds. So what we do is we find all of these derivatives, and then we multiply them with the chain rule. So we get 4x cubed y, so that's differentiating this guy here with respect to x, partial derivative, and then we differentiate this here with respect to s. So we get times r e to the t. Then we differentiate u with respect to y, we get x fourth plus 2yz cubed, and then we multiply that by y derivative with respect to s, and we get 2rs e to the negative t. And finally, we take the derivative of u with respect to z, that gives us 3y squared z squared times derivative of z with respect to s, which is r squared sine of t. Okay, so that's your derivative. Simplify as much as you like. I'll forego all of that because that's just simple algebra that we've all learned back in high school. All right, so now what I'd like to do is I would like to expand this to implicit differentiation. So in implicit differentiation, we are often given some series of functions, some functions of x and y being equal to some other functions, g of x and y, right? So what we can do is we can rewrite this as f of x, y equals 0. If we move all of the functions to one side, we get some function, which is a function of x and y, and that's equal to 0 if we move everything over to one side. So it technically is a relation in the single variable case, but in the multivariable case we can call it a function. Anyways, if that is true and I want to differentiate f, which is what I do with implicit differentiation, then I use the chain rule and I get partial f partial x dx dx plus partial f partial y dy dx. So I'm differentiating with respect to x here, and y is a function of x because we said in normal calculus in our algebra, y is obviously a function of x, right? And x could also be a function of x. Although dx dx, we can kind of treat that as a fraction. This is equal to 1. So what we get is df partial f partial x plus partial f partial y dy dx is equal to 0. So now what we can do is we can solve for dy dx. If I solve for dy dx after I canceled this, then I get dy dx is equal to negative partial xf over partial yf. So this is a much easier formula than going through all of your algebra and factoring everything out, because all I need to do to find an implicit derivative now is find the negative of the partial derivative with respect to x over the partial derivative with respect to y. Let's try an example. Find the implicit derivative such that we have some x cubed plus y cubed equals 6xy. Well, obviously what we want to do is we want to move this over to this side, so we get f of x and y is equal to x cubed plus y cubed minus 6xy is equal to 0. Now what we do, we use our definition, dy dx is equal to negative partial xf over partial yf. And then if we differentiate both of these, then we get negative 3x squared minus 6y over 3y squared minus 6x. Obviously, we can simplify taking out a factor of 3, and we get negative x squared minus 2y over y squared minus 2x. All right, so that is the conclusion for our multivariable chain rule and how we can apply it to a very fundamental idea from single variable calculus. In the next video, we are going to start talking about vectors again in the context of multivariable functions, and we'll introduce the concept of a directional derivative, and later on we will introduce the concept of a gradient. All right, thanks for watching, and we'll see you in the next video. Bye.